Good morning, afternoon, evening, class, whatever time it might be that you're watching this. Today we're going to go over chapter 1.1, Functions and Models. So this is the very first chapter that we're going to go over from Math 108. You get to see how the class is kind of laid out through this first chapter. If you have any questions at all and aren't able to get it from this chapter, please don't hesitate to reach out to me by email, and I will be as responsive as I can to get back to you. Be sure to try your homework on chapter 1.1 when we are done with the conclusion of this lecture notes. So, first thing you need to know is the definition of function. And get my pen ready. So, a function, as you can see it underlined here, is a rule of correspondence that assigns to each element of one set, called the domain, which is important, exactly one element of a second set called the range, also important. A function can be defined by a set of ordered pairs, a table, graph, equation, or even a verbal description, kind of like a word problem, right? So the domain is the inputs of the function, which will be your x, and the range is the outputs of the function, which will be your y, x and y, right? Therefore, any element x in the domain is called the independent variable. So x represents any element in the domain called the independent variable, while y represents any element in the range called the dependent variable. So x is your independent variable, y is your dependent variable, right? X is also your domain, y is your range. Okay. Now we've got some examples here set up for you. Let me scroll down to see all of them. And the instructions say, for each of the following graphs of functions, find the domain and range. Okay, so we've got A right here. So I'm going to start with D. I'm going to let it be the domain. So the domain represents your x values. Keep that in mind. So I'm going to change my color here just to help you recall. Domain is x, right? Range is y. Now let's look at an A here and see what all values of x we have. Now if I look at this point here, its x value is -5. So the way I'm going to write this domain, I'm going to do a fancy curly Q bracket here. I'm going to write -5. That was the first x that we could have here. If I look at the next point here, I have a -3. If I look at the next point here, I have a -1. And the next point here, my x value is actually 0. This point here, my x value is 3. And this point here, my x value is 5. I'll close my bracket here. So my domain here is -5, -3, -1, 0, 3, and 5. All values that x could be here. Now my range values here, remember that's my y. My range is everything that my y can be here. So if I go back through here and I look at this first point again, my y at this first point is -7. Okay? My y at this next point here is -2. Now my next point here going towards the right is up top here. My y there is a 6. My next point here is a -2. Now I already have -2 written. You only have to put it one time. You don't have to put it every time it shows up. So I've already got the -2 written down. I'm good to go. My point here, my y value here is 5. And my last point here, my y value is -7. So I'm done. I'm going to finish out my little curly bracket here. And my range is -7, -2, 6, and 5. Okay? Hopefully that's easy enough for you. Now, if I look at my table here, my table 1.4, It says -5, -3, -1, 0, 3, 5. Those are all the x values that associate with this a here. So if you notice, technically, if I'd have referred to my table first, my domain are just all these x values, while my range are just all these y values. And you notice we have each of those in there. It's not necessary to repeat them. That's why this -7 and this -7 are both represented by just that -7 right there. Now let's look at B and C. Now, what you'll notice with B is that this line starts here and it's got a point, which means it doesn't continue going. This is where it starts, this is where it stops. It's done here, and it's got a point here, so it stops there. If you notice in C, it has this arrow right here, which means it continues on in that direction. If you don't see that arrow, then it stops. So if I'm looking for my domain for this, remember that's your x values, right? Now my x here on this line starts with a -3. So you can see that this -3 lines up right here. So my x, it starts with a -3, right? And it goes to a +3, right? Because this +3 kind of lines up right here. That's what that is. So it goes from -3 to +3. We've got solid dots on the end, which means it's equal to. So the way I'm going to do is I'm going to put it in interval notation, and it's going to be represented by bracket -3, comma 3, because it goes from a value of -3 to a value of 3 on my x-axis. And it's equal to, that's why we put the bracket. Now if I look at my range here, my range, remember, is my y values. Now this starts here, if I'm looking at it, and this could be a little difficult right here, but I'm going to do my best, absolute best, to estimate it. So looking on my computer, it looks like, I'm going to go ahead and draw the line over to it. See how straight the line I can draw. So it's somewhere between 25 and 30. I'm going to say that it is 28. So my range here on the lower side starts at -28, and it goes up to, let's see, top this out and draw it over, somewhere between 35 and 40. I'm going to say 38. And it is a dot, so it's equal to, so my range is -28 to 38. Now if I look at C, my domain, which remember is my x, so my x here, this arrow indicates that this line continues going to the left hand side forever. So it's very important to see that arrow, which means it goes to -infinity on my x here. Now the key to that is we always put parentheses on the infinities. We never put brackets, we always just put parentheses. So we're going to do parentheses -infinity, because that's where it goes to. Arrow indicates that. And it goes all the way up here to this 4. Now, there's not an open circle on 4. It hits right there at 4, so I'm going to use a bracket to indicate that it can indeed be 4. Now, if I look at my range, which is my y values, now on the low side, it doesn't look like on my y here that I go any lower than where it hits right here at this point. Now, obviously the 4 is the x value. The y value associated with it is actually a 0, right? So, looks like we start here with a 0. And then this arrow indicates that it continues to very slowly go up. Now, it doesn't go up very fast, but it goes on forever as it goes up, which technically means it goes up to positive infinity just very slowly. So I'll represent the range here by 0, infinity. This is a very important concept that several people struggle with every semester, so please make sure you get this. Now, we're going to look a little bit into the domain here and kind of hit you with some principles. And then when you look under your lecture list, I actually have a completely separate lecture on domain itself to help clarify some points with a worksheet. So be sure to go into that worksheet and watch that worksheet at the same time, And make sure, I think I'll leave you some extra examples to do on your own in that worksheet. Make sure you go through those examples and truly understand domain. It is a very key point here in Math 108. So you're definitely going to have some questions even on the final exam about the domain of the function. Now, in this first example, we have y equals the square root of 4x minus 8. Now, when we're thinking about the domain here, and we've got an equation, the way I like to put it is we like to think about the items that x cannot be. Okay, so here I've got a square root, and a few facts we know about the square root are, the main fact that comes to my mind is that I can't take the square root of a negative and get a real number. And we want to stay in the real number classification here. So if I were to try to take the square root of, say, -4, if you've messed with square roots before, you'd know that'd be 2i, which is an imaginary number, because we can't really take the square root of this negative here. It kind of gives us a problem, okay? So we want to avoid any circumstances here in this domain where this x, or this square root, or whatever is under the square root, causes this square root to be negative. So we want whatever's under this square root, this 4x minus 8, we want it to be greater than or equal to 0. Now, it's perfectly fine if it's equal to 0 because we can take the square root of 0. Remember, square root of 0 is just 0. Okay, so it's okay that it's equal to 0. Now all we have to do is solve this inequality. So we'll add 8 to both sides, and we get 4x is greater than or equal to 8. We'll divide by 4, and we'll get that x has to be greater than or equal to 8 over 4. We do have to reduce this fraction, which is pretty simple. 8 divided by 4 is just 2. Okay. Now we are going to want to write this domain in interval notation. If x is greater than or equal to 2, then I'm going to use a bracket. I'm going to start with 2 because x is greater than or equal to 2. And then we're going to go on up to infinity. Make sure you always use your parentheses with your infinities. So that is our domain. Our domain is 2 up to infinity. Now in the second example, we also have a square root here, okay? But this square root is in the denominator as well. Now, obviously, the square root indicates that whatever's in the square root needs to be greater than or equal to 0. But the question that you have to ask yourself is, okay, if it turns out to be 0 here, then I'm dividing by a 0, and dividing by a 0 is not something we want to do, right? If we divide by a 0, we get something that's really undefined, okay? So we're going to kind of adjust our thing here because now we're dividing, okay? And our part that we're dividing by, the part we're concerned with is on the bottom, okay? So what will happen here is this x minus 4 still needs to be greater than 0, right? Because of the square root. But we can't let it equal 0 because it's in the denominator. And if it's equal to 0, we divide by 0, we wind up with something that's undefined. Okay, so now we just have to solve this simple equation. X minus 4 is greater than 0. So I'm going to add 4 to it. I'm going to get that x is greater than 4. Okay, so I write that in interval notation. I'm going to start with a 4. I'm going to go up to an infinity. I'm using the parentheses on 4 because it's strictly greater than 4 and it's not equals to. Okay. Now, in this next example, I have y equals the cube root of x plus 1 plus 3x to the 5th. Okay. Now, I have a root here. But what we'll notice about this root is it's an odd root. Okay. It's a 3. So, with this odd root here, I'm not necessarily concerned about taking the root of a negative anymore. I'm really only concerned about taking the root of a negative when the root is even. Okay, and that's a very important point. Because if I ask you to, for instance, take the cubed root of -8, you can even type this in your TI-84 and check me on this if you'd like. The cube root of 8 is 2. The cube root of -8 is -2. And you're like, okay, Mr. Shipes, I might need some further explanation on this because this makes no sense to me. Well, let's look at -2 said 2 and wrote 3, didn't I? So let's look at negative 2 to the third. Okay, that's the same thing as negative 2 times negative 2 times negative 2. Negative 2 times negative 2 is positive 4 times that negative 2, because I need to bring it back down. 4 times negative 2 is negative 8. So the cube root of negative 8 is negative 2. We don't have a problem with the negative in cubed roots or odd numbered roots. Okay, so if you have an odd root here, a 3, a 5, a 7, a 9, you're not concerned with the negative aspect of it, okay? It's not a problem to have a negative in there or a positive. You're only concerned with even roots. So here, since I'm not really concerned with this square root, and there's really nothing else to be concerned about here because only other thing we have is this 3x to the fifth on the outside, and I can plug any x I want to in there and not really have a problem, then what I'm going to do here, since I don't really have any issues that really arise in this one, is I'm going to say that x can be anything from negative infinity to infinity. I can plug any x that I want into there, and I shouldn't have a problem finding a y for it. Okay? Now, this last example here, I have y equals 2 over 15 minus x. Now, we've done a denominator problem. That was the second one we did. So we are concerned with this denominator here, this 15 minus x. And if we make this not equal to 0, then we shouldn't have any problems. The only problem we'll have is if that denominator turns out to be 0. If we don't let it equal 0, then we don't have a problem, right? If we let it equal 0 and it equals 0 somehow, some way, then we wind up with something that's undefined, and that's going to be an issue. So 15 minus x can't be 0 because we don't want any problems. Okay, so if I add x to the other side, I see that x cannot equal 15. So as long as x doesn't equal 15, I'm not going to have any problems with our equation here. Okay, now if I'm going to write that in interval notation, the way I'm going to do it is negative infinity to 15 with a parenthesis because we don't want it to equal 15, union another parenthesis and a 15 on up to infinity. Okay, so essentially it can be anything but 15. The only point we're really excluding is this 15. All right, I think we're doing well. Let's continue to move on. Page 3. Now, we're going to do some tests for functions here. First one we're going to do is the vertical line test. Okay, so the vertical line test is a set of points in a coordinate plane is the graph of the function if and only if no vertical line intersects the graph in more than one point. Okay, so I have a very simple graph here. This graph only includes points. Okay, so what I'm going to do here with the vertical line test is I'm going to draw vertical lines. Okay, and if this vertical line only ever hits one point, then it's a function. Okay, and you can draw a vertical line anywhere on the graph. Doesn't even have to go to an actual point, but it can hit no more than one point, right? So any vertical line I draw here on this graph is only ever going to hit at most one point. Therefore, this is a function, right? Does that make sense? So, is p a function of x? Yes. Because it passes the vertical line test. Okay, now I'm going to draw a little graph to the side here just to give you another example of the vertical line test that might be a little more interesting to you. Okay, so this is just an additional example for you. Let's see, let me draw the graph with another color here. So if I have a graph that say looks like this, so the burgundy-ish line there is my graph. Now what I'm going to do with this graph is I'm going to draw vertical lines, and every vertical line is only ever going to intersect one point. There's not a place on the graph where this line is going to hit more than one point. Okay, doesn't have to even hit a point, but here it's going to hit at least one point, or only one point, every time I draw a vertical line. Therefore, this is a function. That one's pretty simple. An example of the vertical line test where you wind up with something that's not a function, because I'm sure y'all are interested in that. Just scroll down just a bit. Give me some more space in the margins here. So I'm going to draw another XY axis here and sketch it out for you. So my new graph here is going to look like this. I think you can see now that if I try to do a vertical line test on this, I hit 2 points. Now over here I don't hit any points, which is actually fine, but if I draw a few more vertical lines, I hit it at 2 points just like I hit it at 2 points here. Therefore, because I hit it at more than 1 point, this is not a function. Hopefully, most everybody here has seen the vertical line test at one time or another. Now, we've answered, is P a function of X? And we've actually already given the Y for it as well. So let me change my marker color back to blue. But yeah, we've given the Y as well because it passes the vertical line test. Now, it asks a very interesting follow-up question here. It asks, is X a function of P? And it's talking about this original graph here. Is X a function of P? Now, what you'll notice with the vertical line test is that vertical line is only ever going to hit 1 point. So we figured out that P here, this P is a function of X, okay? And if we look at this, okay, each P goes to an individual X. So this negative 100,000 here, it goes to a 0. Each X here, or each P that we enter here, has a different X. Even if we repeat that P, it has a different X. It doesn't go to the same X, okay? But if we go the other way, okay, listen to me. If we go the other way, so the first way we're going here, this one has an individual X. 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 So P is a function of X because each one of these entry points has an individual X, okay? But if I'm to reverse it and ask, is X a function of P? Well, if I go this way, 0 is a negative 100,000. But if I go this way, 3,000 is negative 100,000. Now I have a problem because I have two values that have the same ending value here. And if that's the case, then you don't have a function. Okay, so P is a function of X, but X isn't a function of P because it didn't work in a one-to-one function or one-to-one manner on the way back. No. Why? Because it is not one-to-one. Okay. Now, let's look at some function notation here. Okay. Try to change my color back to blue. It's my standard color. Now, function notation, we have y equals f of x, which means that the variable y is a function of variable x. Okay. So, if I'm looking at this, I've got the function f of x equals 4x squared minus 2x plus 3. And my instructions here ask me to find f of 3. Now, if you'll notice that 3 is in the same spot that x used to be in. What that means is I put that 3 in everywhere I see an x in my equation. So, 4 times, okay, there's an x there. That means I need to put a 3 there for that x, and I need to square it. Okay, minus 2. Oh, there's another x. So I need to put a 3 in for that. Plus 3. Okay, that 3 was already there. Not the same 3, just a 3. Okay, so I have put in this 3 everywhere there was an x in this original equation. Okay, now it's pretty simple. All I have to do is kind of solve it out. Remember, you'll use your order of operations here. Okay, so what I need to do first is my parentheses are exponents. So my exponent here goes with this parentheses. 3 squared is 9. Now I can go ahead and multiply this next step as well because it's individualized. So I have 2 times 3 is 6 plus 3. 4 times 9 is 36 minus 6 plus 3. 36 minus 6 is 30. 30 plus 3 is 33, and there's my answer. Now, I'm going to do the same thing with negative 1. Everywhere that I see an x in this original equation, I'm going to put it negative 1 now. So I'm going to go 4 times negative 1 squared minus 2 times negative 1 plus 3. Okay. Now, negative 1 squared is positive 1, so I get 4 times 1. Negative 2 times negative 1 is positive 2 plus 3. 4 times 1 is 4, plus 2 plus 3 is 5. 4 plus 5 is 9. And I'm done. It's pretty simple. Now, figure 1.14 shows the graph of f of x equals 2x to the third plus 5x squared minus 28x minus 15. We want to use the points shown on the graph to find f of negative 2 and f of 4. Okay, so we've got our equation here, right? So I could do like I did in the above examples and plug the negative 2 in and the 4 in, but it also supplies me with the graph. Okay, and if you'll notice here, the graph, it also gives you the equation in the graph, if you want to see it, but it gives me the points in the graph. Now the points that I'm looking for here, I'm going to write them to the side, are f of negative 2 and f of 4. Now what it means here, remember, is that negative 2 needs to go in for my x. So if I go to negative 2 on the graph, wherever it hits this line right here, oh, see that point right there that I'm coloring in? That is the point that I'm looking for. So x is negative 2 there, and my f of x, or my y there, is 45. So my answer is simply 45. I can do the same thing with 4. I can go to 4 on my x-axis. I can go up and see where the graph hits at 4. Okay, the graph hits at 481, which means my f of 4 is simply 81. Okay, now I can follow it up just like it says right here, and I can use the equation to find f of negative 2 and f of 4. And if you do that, that's perfectly fine. But if you're given a graph with the answers on it, why not choose the easy way out there? But I'll go ahead and do it for you. F of negative 2 equals 2 times negative 2 to the third plus 5 times negative 2 squared minus 28 times negative 2 minus 15. Okay, I'm going to simplify this. Negative 2 to the third is negative 8. So I get 2 times negative 8. Negative 2 squared is positive 4. And let's see, negative 28 here times 2 should give us a positive 56 minus 15. Now, 2 times negative 8 is negative 16. 5 times 4 is 20. Now, 56 minus 15, I'm going to go ahead and do that. That is a positive 41. And now all I have to do is put these numbers together here. Let's see, negative 16 plus 20 plus 41 gives us a 45, which is exactly, if you notice, what we got from our graph was a 45. You can do the same thing for f of 4. And I'm going to leave that as an activity for you to do on your own if you would like to try it. Okay? You should, to check yourself for that one, you should get 81 if you plug 4 in for your x and solve there. Okay? Now I'm going to give you the definition of a mathematical model. It is a functional relationship that includes not only the function rule, but also descriptions of all involved variables and their units of measure. So the example I like to give for this is the example of changing from Fahrenheit to Celsius. Okay, so F equals 9/5 C plus 35. That is the equation for changing from Fahrenheit to Celsius. And obviously you could back solve to change from Celsius to Fahrenheit, however you want to do it. Okay, so that is just a simple mathematical model, right? Given in words a lot of times, but here it's actually giving you the function, but the function relates back to real life. That's the key there. All right, now something we deal with a lot in this class is aligning data. And you need to really pay very close attention to this in the problem descriptions, because if you don't, it'll cause you to get several problems in this class wrong that are actually really easy if you just pay attention to how they want you to align them. Okay, this example here says public health care expenditures for the period 1990 through 2012 can be modeled by the function E of t equals 738.1 times 1.065 raised to the t, where E of t is in billions of dollars and t is the number of years after 1990. So t is the number of years after 1990. That is the alignment part of the problem. That's the part that you really need to focus on and catch. Okay? So what happens here is they'll give you something. They'll give you a different year to solve for after the problem, right? So in this problem, it says approximate the healthcare expenditures for 2010. But I can't just use 2010. If you notice, the previous problem says what value of t represents 2010. Well, if t is the number of years after 1990, then in 2010, if you subtract 2010 from 1990, you get 20. So the t that I'm going to use for 2010 is actually 20, because 20 years after 1990 is 2010. If you plug 2010 in for t, you're going to get the wrong answer. You need to plug 20 in for t to take into account for that alignment. Okay, so in order to approximate the public health care expenditure for 2010, what I'll do is I'll say E of 20 equals 738.1 times 1.065, and I will kind of exaggerate that bracket so it doesn't look like a 1. And we're going to have to raise that 1.065 to the 20. Now this is a good point in time to use your TI calculator. Obviously this is not something I expect you to do by hand. You have access to a calculator, so use it, which is exactly what I'm doing over here to the side. I don't believe I have to show you how to type this into your calculator. I will show you more complex functions, how to type those into your calculator as we move on throughout the semester, but I believe this is a pretty straightforward one. Now, I typed in 738.1 times 1.065, which is raised to the 20, and I got 2,600.80. Okay, I'm going to round it to 2 decimal places. My calculator gave me way more than 2 decimal places, but I'm going to round it to 2 here. And that's what I get. I get 2,600.80. Now, I've got a few review questions here just to kind of make sure, that we got what we needed to get out of this particular lecture. So, the first one, I have table A and table B. Okay, and what we want to ask ourselves here is, does table A describe x as a function of y, or y not? So a lot of times the standard way of doing this is to ask if y is a function of x. But sometimes we reverse that condition and want to know if it works both ways. Okay. Now remember, for y to be a function of x, each y has to go to an individual x. So if we reverse it here, and we want to know is x a function of y, then each one of these x's needs to go to an individual y. So if I look at -9, it goes to a 5. -5, it goes to a 6. -7, it goes to a 7. We're good so far. We haven't repeated any y's. But when I get here, I get -12 goes to 9, and 17 also goes to 9. Uh-oh, they go to the same number. Now, since they go to the same number, it's not a function. So, does table A describe x as a function of y, or y not? No. So, x does not describe, or x is not a function of y here. So, why is it not? Ooh, saying y so many times, guys, it's confusing, isn't it? But we want to know why y and x aren't a function. So, whew. Getting long in the lecture, right? So x is a function of y. So no, because a value of y is repeated. Okay. So Does table A describe x as a function of y or y not? No, because a value of y is repeated. That value specifically is that 9 here. That 9 is repeated, so we have an issue. Okay. Now, if we look at it the other way, it says, does table A describe y as a function of x? So what we'll do here is we'll go the other direction. This is important. Just because x isn't a function of y doesn't mean y isn't a function of x. You have to look at them both individually. So if I look at it here, 5 goes to negative 9, 6 goes to negative 5, 7 goes to negative 7, 4 goes to 6, 9 goes to 12, 9 goes to 17, and 10 goes to 20. I have no repeated x's here. So because I have no repeated x's here, I do have a function. Okay? So, yes, because no values of x are repeated. Okay, good to go on that one. Now, let's look at table B. Now, table B says, does table B describe x as a function of y or y not? Okay, if I'm scanning down here on my y's, okay, I'm scanning down here on my y's, and I don't see any y's here under any of these lists that repeat. Remember, we're going x as a function of y, we're starting with x going to y, starting with x going to y. None of my y's repeat. So because none of my y's repeat, then yes, x is a function of y because no y's repeat. Okay, now if I look at it the other way, grab me another color real quick. If I look at it the other way, so I go from y to x. What I notice here is none of my x's repeat either. So it actually is a function either way you look at it. So yes, y is a function of x because no x's repeat. This is actually a one-to-one function because each table B represents a case where each x has an individual y and each y has an individual x. It's a one-to-one function. Each one has an individual one to go with. Okay? All right, let's look at 5. 5 says if r of x equals 5x plus 8, find r of negative 3, r of negative 1, and r of 2. So all we're doing here, got r of negative 3. I'm just putting in negative 3 here everywhere I have an x. So 5 times negative 3 is negative 15. Negative 15 plus 8 should give us a negative 7. So r of negative 3 equals negative 7. Now if I want to follow up and find r, let's do it in another color. Keep it kind of separated here. So if I want to find r of negative 1, I do the same thing. I say 5 times negative 1 plus 8 gives me negative 5 plus 8. Negative 5 plus 8 is a positive 3. So r of negative 1 equals 3. And we will do the last one. Oh, I already done purple. Let's do light green. Okay. So r of 2 means I plug 2 in for x. So 5 times 2 plus 8. 5 times 2 is 10. 10 plus 8 is 18. So r of 2 equals 18. And we're done. Now, question 6 here says determine whether the graph in the figure represents y as a function of x. Okay, when we're looking at the simple explanation of y as a function of x and going what I consider the correct way or the normal way or the standard way, y as a function of x, we can use the vertical line test like we learned. And if I draw a vertical line anywhere on this graph, the only part that I really have an issue with is right here because I just hit 2 points. But if I hit 2 points anywhere on the graph, it means it's not a function. So determine whether the graph in the figure represents y as a function of x. Explain your reasoning. So no, it's not a function. Because it fails the vertical line test. Simple there. Now number 7 says, which of the following arrow diagrams defines a function? Okay, so we've got to go from the domain to the range, right? So what I like to do with these, okay, is we're just going to go through them. 2 goes to 3, but 2 also goes to 4. Okay, now if your domain here goes to the same range, do we have an issue? That's the question at hand. Because here we have this 2 and it goes to 2 different things. Now we have to think back and remember that domain is your x, range is your y. We only have an issue with it not being a function if think about this now, if your x is repeated for the same one. So simple way to do this, at least for the, that was a terrible drawing, guys. For the first one is I'm going to draw a graph. Okay. This is your domain x. This is your range y. And we can actually go through and plot these points. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Pencil's skipping on me, guys. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Okay, so if I plot that first point is 2 on my domain and then a 3. Okay. So I've got a point here, but then I also have a 2, 4. Now, what you'll notice when I plot those 2 points is that if I were to draw a vertical line, it would hit both of those points. So, because this x is repeated, like I've been saying, because this x is repeated, it's not a function. So, does it define a function here? No, this one does not. Because in just graphing those first 2 points, the 2, 3 and the 2, 4, I notice if I draw a vertical line here, I'm immediately going to have an issue. So remember, I can't repeat my x's here if I want it to be a function of y. Okay, so y is a function of x. Now, if I look at my second example here, what I see is I've got a 5, 6, a 7, 6, a 3, 7, and an 8, 9. So what you're going to ask me here is, okay, these are obviously okay. They go to 1 each, not a problem. But I might be concerned about this. Okay, so what I'm going to do, or try to do, is erase. There we go. I'm going to erase that line off. And I'm going to graph these new points here. Okay, so if I graph 5, 6, so 1, 2, 3, 4, 5, and I go up to 6, let's see, 5, 6, and I graph that point, and I probably need to add a few more tick marks. So 7 would be somewhere way out here, and then I go up to 6 here. If I draw a vertical line, am I going to hit both of those points? No. So it's not an issue. It's not an issue that y repeats here. It's only an issue that x repeats, and x doesn't repeat. I've got all individualized x's here. I do have a repeat in my y, but it's not an issue because we're looking at a function here, y as a function of x. So, yes, this is indeed a function on this one. Now, number 8, very last one of this particular section, says if a model has inputs aligned so that x equals the number of years after 2000. Now, we've got to align this data, and this is the point that I'm trying to get to here. Years after 2000. What inputs will be used to represent 2015 and 3,457? Okay, so for 2015, I wouldn't just use 15. I would have to align it until years after 2000. Okay, which means what I'll do is take 2015, subtract it from 2000, and for year 2015, I would actually just use 15 as my x. Okay, and that's what I would input into my equation if I needed to. Now for year 3,457, what I'd need to do is I need to take year 3,457 and subtract it from 2000. And what I would get here would be 1,457. And that is what I would use for my x. Okay, so be very careful with the alignments, because if you don't catch it, you'll plug in the wrong thing and you will get a very wrong answer. Now, if you have any questions, concerns, or confused about anything at all in this lecture, please let me know. Reach out to me via email so that I can get back to you and try to straighten out whatever you need me to straighten out. Maybe come back in and clarify some points. I don't know if you don't reach out to me and tell me. Okay. Be sure to complete your homework on chapter 1.1, and I will see you back here for chapter 1.2. Y'all have a good day.